Okay then, let's begin our tour, since we're sitting here in this room, with our random mechanical cascade, more familiarly referred to as our pinball machine, and for those of us who have worked with it for many years, affectionately known as Murphy, after the laws that it seems to obey. It's basically a statistical demonstration device. You see machines like this sometimes in science museums. They indicate how random processes produce a typical bell-shaped or Gaussian curve. In this device, there are some 9,000 of these little 3/4-inch marbles that go trickling around, carried up through a conveyor belt. They will come down from the funnel at the top, bounce around, hitting the different pins and each other, and eventually fall into one of the 19 collecting bins at the bottom. Each of these bins is outfitted with a little photodiode that counts the ball as it comes through and records that count not only on a display at the bottom of the bin, but also ships it to a computer file for future processing. Now, by chance, we would expect to see a mean of this Gaussian distribution of about 10, with a standard deviation of approximately 2 bins. That means that 95% of the balls are going to be falling within the middle 5 bins on the device. Now, this machine does have some long-term drift. It is a mechanical device after all. Wear and tear on the bins, on the pins and on the balls produce gradients in over many months or years of operation. The machine does have sensitivities to such factors as temperature and humidity. When it's damp, they tend not to bounce quite as briskly as they do when it's dry. And all of these factors have to be taken into account when we do our statistics. We can't talk about a theoretical distribution here, even though we know that the mean will center somewhere around bin number 10, because it will vary slightly. We have to talk about an empirical distribution. And so the way the protocol works is the operator sits over here on the couch and generates sets of 3 runs. One run would be reflecting an intention to get more balls to go to the right. One would be an intention to get more balls to the left. And the third one would be a baseline where the operator isn't attempting to do anything. So as you can see, intentionality becomes the primary variable that we're looking at. We would then compare the right-going and the left-going runs and see if indeed the mean was higher in the right going than it was in the left, and then we would do it again and again. Obviously, the order of the efforts would be interspersed. Sometimes it would be a right-left baseline, sometimes it's a baseline left-right, etc., assigned by some random process. And an experimental series would consist of a predetermined number of such 3-run sets. So in the earliest days, the series consisted of 20 such sets, and that's about 20 hours of effort, since each run takes about 15 minutes to complete. And 20 hours was asking a lot of people. We then shortened the series to 10 hours, and we got quite a lot of data generated under those conditions. Our formal database consists of several thousand runs, where we have these left-going efforts compared with the right-going efforts, and all together we have a very unlikely correlation between operator intention and the mean of the output distribution. Now, once again, I have to emphasize these effects are small. We're talking about a mean of maybe 10.03 or a mean of 9.92. That's not very much. But when those 10.03s or 10.06s and the 9.93s or whatever are corresponding to the low-going or the left-going effort and the right-going effort, those tiny effects add up. And after a while, over thousands of runs, they do compound to a statistically very robust effect that has a probability of occurring just by chance of just a couple of parts in 10,000. By that time, we know that there's this correlation with the operator's intention is probably a very real phenomenon, even if we can't yet explain it. Well, why don't you join me now as you sit here and observe the machine. It's just going to be a demo. We're going to speed it up for you so you can actually watch how that Gaussian forms, how as a result of all of these random collisions of the balls and the pins, we eventually build up to this bell-shaped curve. If we were doing a real experiment, we would be doing this 3 times. But this time we're only going to do it once. If you want to sit back and imagine that you're trying to move the balls to the right or the left, that might make it more fun for you. But this is what the experiment is like. We would start this, and it does make a bit of a racket.